Today, we're going to explore and understand electric motors, and we're going to do it by building an electric motor and studying how it works. We'll then apply this to understanding how more complex electric motors work. All we need to get started is a AA battery, a screw, a piece of wire, and a rare earth magnet. You'll want a piece of wire just long enough to reach from the top terminal of the battery all the way down to the bottom of the screw, where we'll also place a magnet. This is a neodymium magnet and pretty strong. The stronger the magnet, the faster the motor will spin.
Very difficult. I'm actually squeezing it very hard and I can't get it off of these pliers.
I'll put some black lines on the magnet just so we can see it spinning a little bit easier.
So this is actually most of the motor that's built right now. We have a AA battery. We have a magnetized screw that's held onto the battery because of magnetic forces. And obviously it's attached to the magnet down here. What we do is we take one side of the wire, attach it to the positive terminal of this battery up here and just kind of hold it with our finger. The other guy, we're going to reach down below and actually touch the magnet itself. Now watch carefully what happens at the moment we do this touching here, right down here on the magnet. You can see right there, the whole entire apparatus starts to spin. It'll slow down due to friction, and we can just, when we're ready, we'll touch it again. And we see that we've got a nice, good speed going. You can see this guy's spinning pretty rapidly, in fact. Actually, it's spinning so fast you can't see the black lines that I painted on. Whenever we slow down just a little bit, you'll probably be able to see those.
Now, as awesome as this is, we want to now kick it up a notch and make it look even more impressive.
Here what I have are two light-emitting diodes. They're clear. They actually shine blue light. And here we have a very thin battery. Now, if you hook this guy up in the proper direction, you can see that you have a blue light that goes in there. Now, if you accidentally hook the LED up backwards, nothing will happen.
LEDs act as one-way valves for electricity.
Just flip it over until you see the light coming out. And of course, I've got another one here. So you see in this case, I've got two blue lights. If I accidentally hook that one up backwards, I've got nothing. That's just the way these little diodes work. So just hook it up until you see the two lights. So what I would really like to do is go ahead and hook this guy up like this and then stick it to the bottom of my magnet. Just like that. Now I've got a light that is on. The magnetic force is holding it to the battery. That's all that is. Instead of putting glue there or something, I've got that covered there. And then I'll take another one like this and I'll stick it through. I'll put these guys on, kind of hold them with my fingers, right, like this. And then I'll take this guy and I'll sandwich it in like this. So here I have a little helicopter looking thing. That's kind of neat. I've got two lights that basically are attached and held like this on the bottom. Now, what I'm going to do is hook it up exactly like this. So I have exactly the same contraption. It's just that I've got two lights that are now connected there as well. So let me go ahead and hook the top together, and now I'll touch my magnet. And if I do it right, I've got a nice little light show. And if you're patient, you can get this guy spinning really, really fast. Of course, if you have everything centered properly, everything balanced properly, you can get this thing going really nice. And if you turn the lights out, this looks really impressive in the dark as well. So notice the direction this thing is turning right now. When you're looking down, it's turning clockwise. Now let me show you what happens. Since this force that actually pushes the magnet is dependent on the current that's going in the wire, and it's also dependent on the magnet, if we flip the magnet over, that's all I've done, flip the magnet over, then what should happen is it should spin the other way. So instead of clockwise, it should spin now counterclockwise. So let's see if that actually happens. So let me put this guy here, I'll attach this guy, and then I'll attach that to the top, and now let's hook it up, and let's see. And now it's spinning the opposite direction. It's spinning counterclockwise. And I'm getting a nice little spin out of this guy here. So there you go.
Now the question we need to answer is, how does it work? At the moment we connected the wire from the top terminal of the battery to the magnet, an electric current started to flow through the wire into the magnet and back through the battery. The magnet itself was in the circuit, and electric current was flowing on the skin of the magnet as part of the return current. Of course, during all of this, there's a non-changing magnetic field emanating from the magnet at all times. It turns out that magnets only exert a force on moving electric charges. So any electric current immersed in a magnetic field feels a magnetic force, but that force is always perpendicular to the electric current flow. Because of this, the magnet tends to feel a sideways force which tends to turn the magnet, and that's how the motor works. More complex motors work with multiple windings to amplify the effect, but it's the same magnetic force principle that turns all electric motors.
Today we're going to do a really incredible experiment where you're actually going to be able to counteract the force of gravity or defy the force of gravity with very, very simple materials. So here's what you need to do. You need to get yourself a copper pipe. Now you can get these from the hardware store. Almost any hardware store you could find copper pipes of different dimensions. So this is a regular old copper pipe. It is hollow in the middle. You'll also need a magnet. Any kind of magnet will work. This particular kind of magnet is called a rare earth magnet, or a neodymium magnet is another word for it. It just means this magnet's very strong. The stronger the magnet, the better this is going to work. Now before we get started, I just want to show you really quickly how strong this magnet is. This is a pair of pliers here. Whenever I attract it to the pliers here, you can see that it's attracted there here. When I grab it and try to pull it off, this magnet's quite strong. And that's because of the special way that these magnets are made. You can buy these magnets for a couple dollars online. Just type in neodymium magnet, or you can type in rare earth magnet and you'll be able to find them. Now the interesting thing here is copper is not magnetic. Copper does not react to magnets. So this magnet, as strong as it is, you can see there's no trickery going on here. This magnet just falls right off. Now you could see a minute ago how strong it was when we attracted it to the pliers over there. It's a different metal. Some magnets or some metals are magnetic and some are not. So what we're going to do is just cut right to the chase. As you can see, this is a hollow tube. There's nothing inside of it. There's no trickery here. It's just a solid copper pipe. Now, before we get started, I'm going to show you, here's a copper penny. So the reason I'm using this penny is because I want to show you, to get you used to what this is going to look like when we drop something through this tube. So listen for it very carefully. It goes right down and it pops out the other side. And we'll do it one more time just to show you. It goes right down there, maybe 1 second or so. We'll go right one more time, maybe 1 second or so. So let's put that to the side. Obviously that's just a penny, that's not magnetic. Here's our magnet, but we already said this is not magnetic at all, right? Now let's see what happens when we drop a magnet inside. And listen, watch carefully. Look at that. It took a few more seconds, didn't it? Let's count as we do it. Here we go. 1, 2, 3, 4. About 4 seconds. One more time. Here we go. 1, 2, 3, 4. About 4 seconds for this magnet to go down this hollow copper tube, when it takes a penny, roughly 1 second to fall through. How in the heck can that happen? That is really almost magical. If you show this to anybody, they will do it. They will do it again and again and again and completely be astounded. At first you think it's a trick. You think maybe I've coated the inside of this tube with something that's magnetic. But when you think about it, that doesn't make sense. If this magnet, look at these pliers, if this copper had any kind of magnetic lining, or if it was a trick or something, the magnet would just stick to it. It wouldn't fall down. But you can see clearly whenever we do this experiment that the magnet is kind of tumbling and it's just going slower. It's just falling slower than it normally would. Now to bring this home even more, I have another one of these magnets. It's identical. You can see I have two of these guys here. In fact, there they go. They attract together. They're the same magnet, right? Same size, same everything. And to bring it home even more, what I'm going to do is drop one of them through the copper tube, and we'll drop the other one through this clear plastic tube that I have. And this clear plastic tube is the same height here. So what we're going to do is lift them off the table, and on the count of 3, we're going to see which one hits first. 1, 2, 3. And you can see that the guy coming through the plastic tube falls straight through. The guy going through the copper tube takes a lot longer. We'll do it one more time on the count of 3. 1, 2, 3. And there you go. You can see the difference there. So now it's time to talk about how this happens, because it seems like magic. What you need in order to understand how this works is two pieces of information that most people just don't know about how magnets work and about how electricity works. Once you understand those two pieces of information, then how this thing works is very easy to understand. The first piece of information is, well, I guess there's three pieces of information. The first piece of information, you have to know that copper conducts electricity. We all know this because the wires in your house are all made of copper. Most wiring is made of copper. It conducts electricity. You might say, well, how does electricity have to do with any of this? This is the magnet. Well, when you start studying electricity and magnetism, you're going to find out that magnetism and electricity are really, really closely related. In fact, you can use magnets to generate electricity. And that's exactly how power plants work. When you have a power plant, you have a generator. We've probably heard of a generator, right? So what happens is you have, if it's a hydroelectric plant, you have water that's turning a generator in a river. Or if it's a coal plant, you're basically using the coal to heat up a bunch of water into steam, and that steam turns a generator. Well, if you cut open a generator, what you're going to see is a bunch of magnets and a bunch of copper wire, and somehow that arrangement creates electricity. The bottom line is, if you have a magnetic field, which is what is invisible and it's surrounding this really powerful magnet, it's going through my fingers right now, it's called a magnetic field. If you take a magnetic field and run it across a piece of copper, if you move it across a piece of copper, then what you're going to get is electric currents generated in that copper. And that's how our generators work. But the same thing is happening here. So as the copper, as the magnet is falling, gravity's pulling it down, the magnetic field is moving through the copper and it's sliding across the copper. That motion generates electric currents inside this copper pipe. They just kind of circulate around as the magnet is falling. So that's fact number one. When you have a magnet and it moves across a copper conductor or any conductor of electricity, you have an electric current, a little bitty tiny currents basically inside of that conductor that are generated, right? If you could somehow peer inside, you would see those currents. That's fact number one. Fact number two, which is separate, is that any time you have an electric current flowing in anything, that electric current also produces its own magnetic field, right? So what you have here is a two-stage process. When we drop the magnet in, you have electric currents generated in this pipe, right? That's part number one. The second part is those little bitty tiny electric currents are generating their own little tiny magnetic field. And here's the punchline. The tiny little magnetic field generated by the little tiny currents in there are repelling this magnet that's falling and trying to prevent it from going any faster. They're basically trying to slow it down. So as this thing falls, little tiny electric currents are generated in the copper. Those tiny electric currents are making its own magnetic field, which are pushing up against this magnet. So yes, this copper is not magnetic, it's not repelling, but as soon as it starts moving, a tiny magnetic field is generated in here that pushes up on that magnet and slows it down. And that's why, instead of a penny, which takes about, one second to go through here, this guy takes 1, 2, 3, 4 to come out, right? Now that's part number one of what I wanted to show you today. Part number two is I wanted to get a larger pipe. So you can actually kind of see this pipe is exactly the same size as the other pipe, except that it has a larger diameter. Here I have a larger diameter magnet, right? Here I have a larger diameter magnet that I'm going to place inside of this guy. Let me ask you this. Do you think this effect is going to be better or not as good in this particular case? The answer is it's going to actually work better. Let's just see if that is true. Let's drop it in there and we'll just count. Here we go. On your mark, get set. 1, 2, 3, 4, 5, 6, 7, 8. And it finally dropped out. 8 seconds, right? 8 seconds compared to about 4 seconds for the other one. Why do you think it works better? It's because whenever these little electric currents are generated, they're stronger, basically. They're stronger if the magnet that's falling through is physically closer to the conductor. So you can see this magnet here is almost exactly the same size as this conductor. It's very, very close to this conductor size, okay? So that means the magnetic field, as it falls, is going to be stronger, and it's going to generate better electric currents, and that's going to push more strongly on this guy. Now for our grand finale, we'll do it both times. Here we have our plastic tube, here we have our copper pipe, and what we'll do is we'll just drop them both in, and we'll count them. We'll drop them both in sideways like this, just to make it fair. So here you go. On your mark, get set. 1, 2, 3, 4, 5, 6, 7, 8. And it finally falls through. And you can see a dramatic difference. So the bottom line is, for this effect to work, you need a magnet. The stronger the magnet, the better. You need a copper pipe, and the effect works better if the diameter of this magnet that you drop is very close to the diameter of the copper pipe. You can amaze kids with this. You can amaze adults with this. It's something that most people cannot fathom how it works, because this magnet here is not attracted to this copper pipe. But what's actually happening is once that magnet starts moving, a magnetic field is generated from those currents in that copper that are generated, and that magnetic field pushes up on the magnet. So go and get these materials. You only need 2 materials, very easy to find, and you can do a really, really neat experiment that demonstrates how magnets can interact with conductors and create electric currents and create magnetic fields, and it's a real hands-on way to see how that works.
Learn anything at mathandscience.com.
Today what we're going to do is learn how to work with birthday balloons, something that you would blow up for a birthday party, and we'll learn how to put these balloons directly into a candle flame and have them not pop, have them not melt and pop the balloon. So it's very impressive, it's very easy to do, and we'll learn the science behind what makes this happen. Now we will have a candle in this experiment, so you need to make sure and get permission to do this experiment, get some help, and always have your safety glasses, which I have here. So we'll put those on, and we'll go over what we need for this guy. All you need for this experiment is a candle. A very small candle will do fine. You'll need a cup of water. You will need a couple of regular old birthday balloons. I have 2 of them here, and we'll show you why I have 2 of them in just a second. And you can tie these balloons, with your fingers, or if you're lazy like me, you can use paper clips to hold the ends of the balloons closed. All right, so what we'll do is go ahead and get set up here. We'll put the water to the side, put the balloons to the side, we'll put the candle front and center, and we will light the candle. So let me go ahead and do that first. All right, so it just takes a second to go ahead and light the candle. Candle's lit. And the next thing we're going to do is we'll show you what happens to a regular old balloon whenever you put it in here. What do you think is going to happen? Well, if I blow this up and I put it on top of that candle flame, the hot air is going to go. It's going to hit that. Rubber. It's going to melt it, little hole, and then pop. The balloon goes pop. So let's go and check that out. Let me go and blow this up. All right, so there we go. So I'm going to blow it up. Now you can tie it if you're really good at tying balloons. Tying balloons can be difficult, so if you want, you can just, once you get it blown up, you can just twist it a few times like this. So I've got a nice little twist at the end, and then grab one of my paper clips there and just put it right on top of that guy. And if you've done it, nicely, you should be able to hold the end of it and just kind of keep it closed, and that paper clip should keep it closed. All right, so what do you think is going to happen? If I put this guy right on top of this candle flame, it should pop, right? So let's check that out. So we'll put it there. Let's see how close we can get before it goes pop. A little bit down, and there it goes. It goes pop. So we were just a few inches away from that balloon. That's why it's important to wear your safety goggles too anytime you have something kind of popping like that. So the candle flame put heat into the air. It didn't even touch the flame. The heat that was coming up off the candle flame went directly to the rubber, made a tiny small hole in that rubber because it melted it, and then as soon as it made a small tiny hole, the whole thing just kind of pops, right? So that's what we kind of expect. So let's go and relight the candle. It looks like our balloon actually put out our candle flame. Now, the second time we do it, that's why we have 2 balloons. First time we show you what it looks like regular. Now, I want to do the same thing again, but now what we're going to do is put a little bit of water in our balloon. We're not going to fill this balloon with water. We're going to put a little bit of water in it, maybe even less than half a cup of water. So what I'm going to do is just pour a little bit of water into the bottom. So now I have a little bit of water. I'm going to put a little bit more. I would guess, well, maybe that's like probably 4 or 5 tablespoons of water really is all it is. Okay? So we're not filling up the water, we're just putting a little bit of water in the bottom of the balloon. Now let me go ahead and blow it up again. Now we're going to go ahead and twist this guy up, just like we did the last time, nothing different. And we'll put that paper clip on there to hold it there. Now what we have is a balloon, and if we've done it all correctly, we should have water sloshing around the bottom of this balloon. Now, before we do the second part where we put the balloon on top, I'm going to put my candle on a little plate. The balloon shouldn't pop, but just in case it does, we want to have a little plate there to try to catch at least some of the water. So what you want to do is you want to put, you know you have the water in the bottom of the balloon, and you want to put it right on top, in the same place we had before. And let's go ahead and give it a good count to 5 and see if we can get this balloon to last. So let's go down. 1, 2, 3, 4, 5. Now if you put your hand to the bottom, it does feel a little bit warm, but it's not super hot. Why do you think that is? It's because you have water inside of it. So what's happening is the heat from the candle is going into the rubber, and normally it would pop that rubber, but since there's water in it, water is a great absorber of heat, so to speak. So what happens is you put the heat into the rubber, the water is sitting right behind the rubber on the other side. It's absorbing all that heat, so it's kind of pulling it in. It loves to take in that heat, and water can absorb a lot of heat, you know, by itself. So it kind of takes the heat away from the rubber, and that kind of prevents it from popping. So let's go ahead and try it one more time and put it even closer. We'll go even a little bit lower. Right on top. And you can see that definitely it would have popped by now. And put your hand on the bottom, not too warm. And so for our grand finale, what we'll do is we'll put the balloon directly on top of the glass and see if by putting it right on top of the glass we can actually smother the candle. So that'll be sort of the grand finale. All right, and so we'll just put it right down there. And the candle is out. So that is a good experiment in basically heat conduction. We did the empty balloon, and that showed us that if you have an empty balloon, you put it on top of a candle flame, it's definitely going to pop, and the reason it pops is because the hot air that's coming off of the candle basically melts a small tiny hole in the balloon, and then it pops. And it really, the other balloon, I mean, it was very, very, very close to the actual candle, but it wasn't even touching the candle before it popped. In this case, what we did is we take the full balloon and we put some water in it, and then the heat goes from the candle into the balloon, and then it goes into the water that's sitting right on the other side of the balloon. That water is pulling that heat, conducting that heat away from the rubber. So the bottom line is the rubber is not able to get that hot, because as soon as it does get a little bit hot, the water sucks that heat away. So that's what causes the rubber not to melt and not to pop. And you know, we have a bonus science experiment here. What we did is we kind of put the balloon directly on top of the candle, right, to smother it, just to show you how close we could get to it. And look what happens now. If we lift this balloon, try to lift it off, we can actually lift the candle. Now, why do you think that's the case? It's sort of a bonus science experiment. What happens is the air that's directly around that candle down where the flame is very, very hot, right? So we put the balloon on top. Now, before we put the balloon on top, the air is being pushed away from that candle flame. What happens to things when they get hot? The air wants to expand. When things get hot, like air, it tries to go and push farther out and expand. When things get cooler, they try to contract. So since this candle is hot, the air around that candle, when it was burning, is being pushed away because it's all trying to expand because it's getting hot. Now, as soon as we put the balloon on top, we smother the candle. There's no more heat. The air that's trapped in between the balloon and the candle starts to cool down. So it was being pushed away when the candle was on, but once the candle was extinguished, that air that's trapped in there tries to contract and get smaller. And when things get contract, it makes low pressure. So there's atmospheric pressure out here pushing on everything, and inside between the balloon and the candle is a little pocket of air. Since it's trapped, and since it cooled down, it actually has low pressure. So you have low pressure, which means low pushing, inside of here. You have outside air pressure pushing on it. So what's really happening here is the outside air pressure, the atmospheric pressure, is holding these things together. We have air pressure pushing up on the bottom and pushing on the balloon, holding it together. We have low pressure on the inside. It's not able to fight it. So the outside air pressure wins and it holds everything together. The only way to get these things off is to kind of pop it off like that. I'm Jason with scienceandmath.com. I hope you've enjoyed this experiment. Go get yourself the materials needed. Very simple to find things. Candle, couple balloons, couple paper clips if you want, goggles, of course, and most importantly, adult supervision. Go try it for yourself. Go explore heat conduction and show yourself how you can actually take a regular old balloon from a birthday party, put it right on top of a candle flame, and it will not pop.
Learn anything at mathandscience.com.
Today we're going to build a very simple electric motor that you can build really out of 3 components. Take you about 10 minutes, and I guarantee you once you know how to build it, put it on your desk or put it on the table and just kind of let people watch it. They'll kind of stare at it and say, well, how does that work? Because it looks really neat and it just kind of sits there spinning over and over and over until the battery runs down. So let's learn how to build it. It's very, very simple to do. All you'll need to build this little guy is a AA battery. Go and get a new battery. You'll need some copper wire. This is solid copper wire. There's no insulation on it. It's just sort of bare copper. And you will need a magnet. This is a rare earth magnet called a neodymium magnet. You can find them usually at the science supply store, or you can find them certainly online. Usually just cost a few dollars for a magnet like that. You can type into a search engine rare earth magnet or neodymium magnet and find these guys. So believe it or not, that's really all that's required to build this, and there's many, many ways to build a motor. There's many, many designs for motors, but this is really one of the simplest ones and one of the neatest ones. So we want to go ahead and put our safety glasses on just so we have them, just so we can be safe. And I have a pair of scissors here. These are sort of shears that I'm going to use to cut this wire. So really, again, this is solid copper, and you can sort of see the texture of it, so to speak, how much it bends. I mean, it's very easy to bend into whatever shape you want. So the exact size, diameter, and all that doesn't really matter. You just want to get some sort of wire that you're able to bend. And by the way, this would work if you had some kind of really solid copper wire with insulation on there. It should work. You'd have to make a few modifications to it as long as you have the copper in the middle. So go ahead and make a quick cut, and then we will just sort of put this off to the side. We don't need that anymore. And basically what you're going to do is you'll just take your battery and your magnet and you will stick the magnet to the bottom of the battery like that. So that's not going anywhere. And ultimately what the entire device will consist of is you'll put it on the desk and let it sit there, and this piece of copper that we're about to make is just going to spin around and around and around until the battery goes dead. And we've already built a different type, very similar but slightly different type of motor in this experiment series already. They're both really neat. This one, to be honest with you, I kind of like it a little bit more because you can sort of sit it down and just let it do its thing, and just people can just watch it. So what you want to do is take your long strand of wire, and basically you want to fold it in half. So you take it like this, and by the way, there's no hard and fast science to this. I mean, as far as how to build it, there's science as far as how the motor works, but there's no one way to exactly do it, I guess is what I'm trying to say. You'll see very quickly how we're basically building the thing, but as far as like the exact way you fold it, the exact way you shape it, the exact way that you form the thing doesn't really matter that much. So what you're trying to do is basically make a little point here, and then once you get it into a point like this, you want to sort of make almost like a golden arches out of it, like this. So we're going to turn it upside down, and we're going to bend it like this. Or you could look at it as a bird, you know, a little flapping bird, whatever you want to do. But basically you want it to be in a little point like that and kind of coming up sort of like a golden arches. Now, the reason we're doing that is because really what you want to do is you want it to balance on top of this battery the way we have it here. Okay, you want to balance it. And the reason is because it's going to just go around and around in a circle like that. Now, one thing you can help with that, I didn't put this in the materials list because it's optional, but if you just get yourself a little screw, and here in the top of the battery here, if you just sort of push on it very gently with a screw like this, you can make a little indentation. You don't want to do it too much. You don't want to, rupture the battery, but just do a little indentation there, right on the top, and that can help because, like I said, ultimately this thing is going to be spinning around and around, so a little indentation there can sort of help it stay on track, so to speak. Okay, now what we're going to do is, let me go ahead and set it up like this. What we're going to do is have it basically like this. We'll go a little bit higher like this. We'll have it basically like this. Now what we want to do is we want to sort of mark where the magnet is at the bottom. So if we sort of put it there, the magnet is going to be there. So keep your finger there, and what you want to do is sort of bend that in like this, right? You want to bend that in. You want to do the same thing on the other side. And you can sort of see what I'm talking about when I say there's no exact science to exactly how to build these things. It's going to be your own little creation when you're done with it, right? So if we put it like this, we should have these two little pieces crisscrossing right on top of the magnet. Basically, you're making a circuit where the electricity can flow out of the battery and down through the magnet. And of course, since the magnet's connected to the other part of the battery, it just kind of makes a circuit of electricity like this. Okay, so what we want to do is, as we place this guy on top like this, we want to be able to touch the top and have the bottom two pieces touch the magnet down here. And we'll let go. And you can see it already sort of started to spin. So you can sort of let go, and you can see it spin and it sort of falls off. So this is the basic motor. You can sort of see it spinning as we do our thing. The only problem is it's really not stable, because since the bottom here is sort of open, as soon as it starts spinning, a lot of times it's going to fall off, and that's no fun. So what you really want to do is sort of bend the bottom here. If you can kind of see, down by the magnet, what you really want to do is bend these bottom pieces to kind of curve around your magnet and sort of grab onto it. And that can take a few minutes to do. So I've already done it basically right here. And you can sort of see the difference. So here's the one I just created here. You want to kind of curve these two pieces down here. And so that's what I've done in this one right here. You can sort of see this guy curve down like that. So if you do that, then what you're going to have is you'll just kind of, you can see how it's kind of loosey-goosey down here. You can just kind of go and slide it on top and touch it there and let go and see what happens here. And we can see that it is spinning nicely, and it just sort of continues to go and go and go. And that's the nice thing about this motor. It's very simple to build, just takes a few minutes, and you can literally have this sitting out on your desk. If you're a teacher, just kind of have it sitting out. If you're just working in an office environment, just grab it out of your desk, put it out, and this thing's going to continue to spin until the battery's dead. All right, now it's time to try to understand exactly how this is working. And the exact details of how it's working, you could use math, you could figure out exactly how fast it's going to spin, the direction it's going to spin, and all of that. And I'm not interested in really giving a math lesson right now, but what I am interested in doing is trying to teach you basically how it works. So what you have here is very simply a wire connected to the top of the battery, the positive terminal of this battery, and then you have that wire coming around and taking the electric current down and dumping it into this magnet. And now you need to know also that this magnet conducts electricity. So when the electricity goes into this magnet, it's allowed to go straight back up into the battery. So you've completed a circuit on both sides really, and you've allowed the electricity to kind of come out and back and come back down into the magnet. Now, what this does is very, very important, is really the key to the whole thing working. The one thing you need to know how any magnet or any motor works, any kind of motor that turns when you put electricity into it, they all basically work the same way. Motors work because of one fact of nature, and that is the following. If you have a magnetic field, and we have a magnetic field around this magnet here, if you have a magnetic field, then if you have an electric current flowing through a wire in that magnetic field, then there's going to be a force on that wire. Okay, that's always going to happen. That's something that you learn when you get into physics classes and things like that, and that's how all motors work. And I'll say it one more time. If you have a magnetic field and then you have a current like flowing through a wire that's placed inside that field, there's going to be a force that's going to pop up and act on the wire. Right? Now in this particular case, the direction of the magnetic field, that's all invisible by the way, you can't see the magnetic field, but it's here. the direction of the field and the direction of the current line up in such a way to cause a force to want to push this guy, which direction? In the clockwise direction. So the current is flowing down through and going in this direction. The magnetic field is down there around that magnet, and the two directions of the magnetic field and of the current tend to put a force on this side of the wire pushing this way, and on this side of the wire pushing this way. So what you get is a net turning effect. So the force on this wire is going that way, the force on this wire is going that way. One thing that might be kind of nice to see is sort of like a picture. This magnet that's on the bottom is basically like a cylinder like this, right? And you can't see it, but there is a magnetic field that's coming around there. So the direction of that magnetic field comes from the top face and kind of goes invisibly out and kind of comes back to the bottom face, and it has some kind of direction to it. That's why I have arrows here. So the magnetic field over here kind of circulates like this, right? So, you know, I could keep drawing lines, but I don't want to clutter up the drawing. Basically, you have, you know, going from the top, coming down to the bottom, going to the top, coming down to the bottom. And it's in 3 dimensions, so no matter how you look at it, there's always an invisible magnetic field coming from the top and going to the bottom. But mainly what I'm wanting to show you is that there's a direction to this magnetic field. There's a direction to it. If you take the magnet and flip it over, the direction of all these arrows is going to be backwards, right? You can kind of just sort of see that. If I turn the magnet upside down, then the arrows are going to basically point the other direction. So what this means is that if in this configuration, if when we have the magnet like this, if the force lines up to want to turn this guy in the clockwise direction, what do you think is going to happen if we flip the magnet over? Right? So let's first of all look at it exactly the way we built it, like this, and we can see that the motor wants to turn in the clockwise direction. All right? So what we'll do is we'll flip the magnet over, that's all I've done, put it back into place. And basically what we're doing is that the electricity is still flowing in the same way. The electricity is still coming out of the top of the battery and flowing down towards the bottom and going into the magnet in the same way. The electricity is doing the same thing, but the difference here is that the magnet is flipped over. So the magnetic field is flipped over, and that's causing the force on these wires to be reverse of what they originally were. I'm Jason with scienceandmath.com. I hope you've enjoyed this segment where we've learned how to build a very simple motor, probably one of the simplest motors that you can build, that you can just build it, put on your desk, and sort of gingerly watch it spin around. Now I'll tell you, if you spend some time and get the bottom of it looking just perfect and get some pliers out and shape it to the circumference of that magnet down there, you'll get a perfect fit, and you can just let it watch go even faster and faster. It's very, very simple to do, but it does take a little bit of time to get that bottom exactly correct so that it's always touching that magnet. So spend some time, play around with it, but even if you don't do that, it just takes 5 or 10 minutes to build this thing. You could literally whip that up while someone's sitting right in front of you and just amaze them and show them what's happening. And never forget, what's really going on here is you have an invisible magnetic field down there, and then you have this battery sending electric current into that field, and anytime you have electricity flowing inside of a magnetic field, there's going to be a force pop up, and in this case that force is pushing the wire, you know, both sides of the wire in different direction, and that's causing the turning motion.
Learn anything at mathandscience.com.
Today we're going to use food coloring, water, and a candle to show how air pressure can actually force water up a column. It's a really simple experiment to do, but actually very impressive. All you'll need for this guy is some very simple things that you'll find from around the house. You'll need a plate, you'll need a candle, and you'll need some food coloring. It doesn't really matter what color food coloring you have, but I chose blue in this case. And then you'll need some water that you can pour, and then you'll need an empty glass. Now you're going to want to make sure that the glass is able to fit around your candle that you're actually choose to use, and you'll see why that's important here in a minute. So what we're going to do is just move this guy over here, put the candle in the center, and then what we're going to do is pour some water into this plate. Now how much water do you need? You really don't need a lot of water, but you want to go ahead and fill it up where you have a fair amount of water, something like this. All right, and then what you want to do is put this candle right inside like this. And of course you want to light the candle, and you want to get your permission from your parents for sure to do this, or an adult, and wear your safety glasses, because anytime we're working with candles or anything like that, we definitely want to be safe. So let's go ahead and light this candle. There we go. Let's let it go ahead and get nice and hot. Basically what's happening here, if you think about it, anytime you light a flame or light a candle, is the flame is starting to grow, and right above this candle is a pocket of air, a whole column of air right above the candle, and this column of air is starting to get hot, okay? So and that's going to be very important for this experiment here. Now the next thing we want to do, while the air is getting hot and while this candle is starting to work itself out, is we want to make this water colorful. The only reason we're doing this is so that we can see the water as it rises up into the glass. So what we're going to do is just put a nice bit of food coloring, probably too much food coloring, but we like food coloring, so that's okay. And just give it a nice gentle stir. Want to be careful not to make a mess here, but want to give a nice gentle stir, okay, so that it's a nice even blue color. So there should be absolutely no way that we would not be able to see this blue water as we do the experiment here. All right, so the next thing we're going to do is take our empty glass, which is the one that we have right here that fits over the candle. We're going to turn it over on top of the candle and push it all the way so that it's sitting inside this water. And I want you to look very, very carefully at the level of the water inside of this glass as this happens, okay? On the count of 3. 1, 2, and 3. Now let's watch carefully. So the candle is going, and the candle is using the oxygen inside of this guy here. It's heating up the air, and then eventually, because of the seal there, the oxygen is all being used up. And then what happens here, look what happens here. As the candle goes out, the water level is rising, rising, rising inside of that cup. And you can see the water level rose probably maybe 1.5 centimeters, something like that. There. So this is a demonstration, again, in air pressure. I can go ahead and take my safety glasses off now that we've actually done the experiment. What's happening here is whenever we light the candle, we said more than once that it's heating the air up, right? And we already talked about in other experiments, when you heat things up like air, they want to expand, they want to get bigger, right? So the air that's sort of in this pocket around the candle, it's wanting to expand, it's wanting to get bigger, it's wanting to push away, right? And so when we cap off the top of it with the cup, we exhaust the oxygen supply. The candle can't burn anymore because there's no more oxygen inside. So slowly the candle flame goes out. Right? Now, as soon as the candle flame goes out, there's no more heat being produced inside of this guy. So the air that was left behind, the air tried to push its way away from the candle. Whatever air was left behind immediately starts to cool off, right? What happens to gases when they start to cool off? They start to get smaller. They start to contract, right? When things contract, we say they have lower pressure. When things expand, we say they have higher pressure. So what really happened here is we made the air hot so that when we capped it off and cooled off the air that was left behind, it starts to contract, and the pressure inside of this glass gets lower because of that. So what we have at the end of the day, once the candle goes out, is we have low pressure inside of this glass. And where's the other pressure at in this situation? We have higher pressure outside the glass because of the atmosphere. We don't feel that pressure, but it's always there. So we have so much pressure pushing on the water all around this glass. It's pushing down, that's atmospheric pressure. And then inside, we created a situation where we have low pressure. So we have a low pressure inside, which means low pushing, high pressure outside, which means higher pushing. So the outside air pressure pushes the water level down, up into the glass. It goes down around the bottom lip of the glass and goes up. And you can see it with the food coloring. The only reason that we used food coloring was so you could see it. So really, you can do this experiment with a candle, a glass, and a plate, and some water, and you don't even need the food coloring. That's just to help you, get a little bit of a kick out of seeing it rise. And you can see that it probably went up a good 1.5, almost 2 centimeters, something like that. So go grab an adult, go get the materials, and show yourself the power of air pressure, that it's pushing on us all the time. We create low pressure inside, high pressure outside, and that forces the water level up into the glass.
Learn anything at mathandscience.com.